You're standing in front of a complex assembly line in a noisy factory near San Francisco. Machines hum in sync, yet the line hiccups unexpectedly. Nise's control systems engineering jumps right into these real-world puzzles, where feedback loops aren't just math, but the secret sauce keeping massive machines humming smoothly. But what exactly makes these control systems tick? And how do engineers tame chaos with precision? Let's unravel these questions, starting with a simple lever that turns entire industries around. Let's crack open one of the oldest but trickiest ideas: feedback. You know it's everywhere, but how does it actually work in controlling machines to avoid disaster? In Chapter 3, Nise shares how Boeing uses feedback loops in autopilot systems. Pilots set a course, but sensors constantly adjust wing flaps to counter wind shifts. Without this invisible correction, flights would veer wildly. It's like having a co-pilot who never blinks, making split-second tweaks, all based on precise feedback data. Imagine walking a tightrope. Without feedback, you'd fall instantly. Your brain reads small sways, tells muscles to react, shifting your balance. Feedback in controls works the same way. Sensors detect deviations, controllers send corrective commands. It's a dynamic, constant dance, a perfect metaphor for why feedback isn't just a concept, it's the art of balance. The ultimate magic is how feedback transforms unpredictability into smooth operation. Nise explains how feedback control made automated assembly lines in Detroit revolutionize manufacturing by slashing errors and downtime. What starts as chaos, fluctuating speeds, variable loads, ends as elegant precision, proving feedback loops are the unsung heroes of modern tech. Next, how do you boil down a messy physical system, engines, pumps, robots, into neat, solvable equations? This translation is where theory meets real-life control challenges. Nise introduces a water tank filling system where inflow and outflow rates determine water level. By writing differential equations for flow rates, students see exactly how changes ripple through the system, like watching ripples from a tossed stone move steadily outward, but this time capturing every detail mathematically. Think of the system equations like translating a foreign movie's dialogue. The messy, real-world behavior gets encoded into Laplace transforms and block diagrams. They're the subtitles letting engineers read and predict system responses long before testing physically, giving control engineers psychic insight into what's lurking beneath the surface. Once modeled, systems behave like obedient dogs trained with treats. You tweak inputs expecting precise outputs, no surprises. As Nise shows, this ability to predict systems in advance means fewer costly failures, smarter designs, and faster innovation. It's why mastering the math behind control isn't just homework, it's unlocking control over reality. Finally, how do engineers design controllers that not only react correctly but anticipate mishaps? Here's the clever dance between stability, speed, and accuracy, where every fraction of a second counts. Nise showcases the practical impact of PID controllers across industries, from chemical plants in Houston to automotive cruise controls in Detroit. The proportional, integral, and derivative actions combine like spices, each balancing the other to achieve smooth, responsive control, no matter how unpredictable the environment gets. Designing controllers isn't just theory, it's a messy, on-the-ground craft. Nise highlights tuning experiments where engineers wrestle with real signal noise, actuator limits, even temperature swings. It's like tuning a guitar in a hurricane. You must find sweet spots that hold up under chaos, ensuring reliable, repeatable performance. Why the obsession with stability? Because an unstable system isn't just a bad day, it's catastrophic failure. Nise traces the development of control standards that made stability a baseline dogma. More surprising, pushing beyond stability to optimize performance led to breakthroughs in robotics and aerospace, proving tame systems can also be daringly fast and precise. Remember our factory line from the start? Feedback loops were quietly juggling every hiccup, equations were their secret language, and carefully engineered controllers kept chaos at bay. That's control systems engineering in action, turning unpredictable messes into smooth, reliable operations. Next time you tweak your home thermostat or cruise at 60 mph, you're living proof of these concepts. Try this. Spot a feedback loop today and think how it's keeping your world stable. Subscribe for more book summaries like this one.